Okay, so at this point we have the gas in the syringe. The reaction has just taken place, and we're going to take the readings from the syringe in order to complete some of our questions. So if we click up on the manual, we see that if we go into the procedure, we have gone through everything at this point, and we're on to the assignment. So the assignment question 1 says record the following: the mass of zinc used, okay, the molecular weight of zinc, the volume of 6 moles per liter of hydrochloric acid, and the maximum pressure reached during the experiment. So what we can do is we can go up to the data window, click on that, and we find out that here are all the chemicals inside the gas syringe. So the mass of the zinc used is easy, it's only 10 grams. Okay, the molecular weight of zinc, that can be found by going to the periodic table. And we see here it's 65.38. grams per mole. Okay, the volume of 6 mole per liter of hydrochloric acid. Is 10 milliliters. Okay, and then the maximum pressure reached during the experiment. And then the maximum temperature reached during the experiment. Okay, so I just had to restart my computer, the website, because the lab actually crashed. Alright, back to D and E. So the maximum pressure reached during the experiment would be the initial temperature displayed on the pressure gauge, and the maximum temperature reached during the experiment is what's displayed on the temperature gauge during the experiment. But both of them are initial. Okay, so the pressure should be just over 181 kilopascals, and the temperature should just be over 308 Kelvin. The final pressure in the gas piston at the conclusion of the experiment is, that's what F is, 101.325 kilopascals. Okay, alright, so on to question 2. Calculate the following: moles of zinc reacted. Alright, so right now we have our answers from A and B. We're going to use those to figure out the moles of zinc reacted. We take the amount of zinc that we have in the experiment, so 0.25 grams, and we divide it by the molecular mass. I'll actually bring up a calculator here on the computer so you can see me do it. Okay, so 0.0032 approximately moles of zinc have reacted in this experiment. Alright, so the moles of hydrogen produced. Okay, so we look at our balanced chemical equation and we see that for every mole of zinc reacted, there is 1 mole of hydrogen gas produced. So the ratio is a 1-to-1 ratio. Okay, and so for the purposes of math, you just take the moles of zinc multiply them by 1 mole of H2 divided by 1 mole of Zn, or zinc, okay, which gives us 0.00382 moles of hydrogen gas. Alright, C. Molar volume of ideal hydrogen gas at room temperature. Okay, final volume in the gas piston divided by the moles of hydrogen gas, expressed in liters per mole. Okay, so to figure out the molar volume here, 2C, that's when you're using your PV equals nRT equation, and you're going to isolate for your V and solve for V. Now, you grab the pressure, or the final pressure in your piston. R is a constant, T is the room temperature, and because it's the molar volume here, not just the volume, but the molar volume, N is going to be 1 mole. Okay? So, you end up calculating that, and you get 24.1235 liters per mole. Okay, and you're going to use that number again in 3. Okay, so don't round it. Or if you want to round it for the final answer in 2C, make sure you use an unrounded value in 3. Okay, so in 3, all we're doing is finding the percent error. Okay, and it talks about going to the background section, so you just click on background, scroll down. Okay, and the molar volume of an ideal gas is 24.5 liters per mole, and that's what I'm going to use in my predicted molar volume. Okay, so the formula is kind of jumbled up here because the window is not large enough, but the formula is experimental molar volume minus predicted molar volume with absolute bars around that. Okay, that's the numerator, and then the denominator is actually, so whatever that ends up being, it's going to be divided by the predicted molar volume. Okay, so yeah, same number. Okay, and then you should get a very small decimal number, like 0.00, kind of small, and then make sure you multiply it by 100 in order to get percent error. Okay, if you're not multiplying it by 100, you're getting a decimal version, and it's not very usable or not very commonplace. Alright, so once you're done calculating that, you should get a percent error of 1.54, or the all the way up to, I think it was 1.62, depending on how you used your data and at what points you took any kind of values. Okay, so the B is in your opinion, so I'm not going to answer that or look at that, but I would say look at every single thing that you were using, any kind of glassware, any kind of chemicals, any kind of tools, and think of anything that may have caused a percent error. Okay, in a computerized lab like this, it's a little harder to see because you can't exactly look at the tools. Okay, everything is very much controlled. Okay, but there is some percent errors, or some errors causing the difference, and so it's up to you to answer 3B. So whenever you have a percent error, or sorry, whenever you have a reason for the error, state your source of the error, and make sure you also cover how this compares to your hypothesis. Okay, so you should have, I would say, what, 3% errors? Oops, wrong. 3% errors. Yeah. Okay, and every lab does have errors, so you can't say there is none. I tried it many times as a student, and it never works. If you have any questions, just email me. Thanks.